Dear colleagues, it's my pleasure to have today at our AI seminar Professor Emilio Porcu from Khalifa University and from Trinity College Dublin. That's a nice continuation of a series of seminars we have where we mix more applied and more, I would say, theoretical work. And I think that the work of Emilio is right in the intersection, probably a bit more theoretical. We'll see what is its inside. So, Emilio, please go ahead.
Good afternoon, everybody. Thank you, Maxime, for the introduction. This talk is about kernel methods in probabilistic learning. In particular, I will talk about Stein discrepancies, where the input space is a compact Riemannian manifold. This is a static version of this talk. There will be a short introduction to a motivation of the problem, and then I will enter into probabilistic learning. I should talk about a parallel between quantization and the importance of Stein methods within quantization and the Bayesian optimization. And then the core of the topic, which contains the methodological proposal, is about Riemannian Stein kernel methods. And if there is some more time, I will talk about future developments and impact of this research. This talk is based on 4 recent papers of mine with these 4 guys. Chris, Mark, and Alessandro are coming from Alan Turing Institute, and François Bachot is coming from Université Paul Sabatier in Toulouse. So these are very recent papers. 2 of them are published, currently published in Bernoulli, one in the Journal of the American Statistical Association, and the last one in the Annals of Statistics. So those are, I would say, theoretical papers, but the structure of this talk is not. I have avoided as much as I could technical development to avoid mathematical obfuscation, and I should try to illustrate, to dig more into the ideas rather than the mathematical development. Of course, feel free to interrupt anytime if there is any question, comment, something that is not clear from this position. So this is a quick sketch of my research interest. The talk of today is about probabilistic learning. You're going to see this red hand several times through the talk, just to locate you within the mapping of the presentation. And these are the recent subjects I've been working on. The first is about kernel methods on graphs, where graphs are implemented to overcome the problem of nonlinear network structure. So I explicitly refer to metric graphs or graphs with Euclidean edges. And I'm interested in the foundational aspects of this deep learning, in particular respect to robustness within the planet of deep learning, statistical robustness, of course. And I've been working several years in the theoretical aspects of spatial statistics. So the essence of this talk stays in this picture, which is taken from a paper by Graf and co-authors. So on the left-hand side, you see a picture of this lady. I think the name is Elena. And on the right-hand side, you see a statistical approximation of this picture using Monte Carlo, quasi Monte Carlo sampling with random weights and with a linear combination of Dirac delta functions, as simple as this. So the problem is how to quantify the discrepancy between the state of truth, which is this realization. You can see this as a realization on some unit square of a function that lives in some reproducing kernel in the space. And this realization is coming from a family of probability distributions. And the question is, how can I approximate the state of truth with an arbitrary combination of delta function, Dirac delta functions? This explains the first part of the talk. So I should talk about statistical learning of a quantity of this kind. So we're learning an integral of a an integrand small f against a probability measure, which I will term as a capital P throughout. And the domain of integration can be anything. When I will come into the more technical part of the talk, this will become a compact Riemannian manifold. And throughout, we suppose that this function f, the integrand, lives in some reproducing Kernel space. We're going to see what it is in the subsequent slides. And when I talk about linear combination of Dirac delta function, this is just the trivial combination with weights. And the way we choose these weights will be illustrated throughout. Once we understand the idea, we should talk about kernel mean discrepancies on Hilbert spaces. And since I'm more interested in the statistical interpretation of the results rather than the machine learning part, so I'm more interested in statistical accuracy rather than prediction, I will talk about the bounds for the worst case error that you can make when you approximate the state of truth with this linear combination of delta functions. And I will explain how to improve those bounds when you use Sobolev kernels. Then I will turn into the Bayesian scenario, where typically, even for practitioners, the typical problem is to get rid of the normalization concept. You never know how to compute it, right? So we want to overcome the MCMC problem by introducing some methods that allow to get rid of this normalization concept. And I will explain how to do that. And this will project ourselves into kernel Stein methods. To give a rough idea of what it means, this picture is quite self-explanatory. So this is my state of truth, the blue curve, which is the probability distribution P. And this is another wrong distribution that I'm using to approximate the state of truth. And what I do is to project the sampling points into some suitable reproducing kernel Hilbert spaces. And the red dot and the brown dot are representing the mean embedding of the first distribution against the second distribution. And then we measure over this infinite dimensional space the difference between distribution in some norm sense. So, as I said before, I'm more interested in the statistical perspective rather than machine learning perspective. And specifically, I would like to reach a reasonable compromise between computational scalability and statistical efficiency, which are notoriously in a trade-off. Then the second part of the talk, you can see, replaces the Dirac delta function with what I call a Stein interpolant. This will become clear through the exposition of this talk. So we use a different interpolant that is not a linear combination of delta function. And this opens to Stein classes. This is a bit more theoretical. I shall try to keep it grounded. Yeah, there is a bit of mathematics involved. Anyhow, I will show that the statistical accuracy of the methods, both exactly and asymptotically. If there is any space for any time left, I will talk about impact of this project for theoreticians and practitioners and upcoming projects. Any questions so far?
I didn't know we know what we are trying to learn, because we need to be confused. For example, do we, on the previous slide, do we learn this F or we learn distribution P?
No, I want to learn this integral.
So F and P are fixed.
Yeah.
But we don't have access to them.
F can be any realization from a suitable reproducing kernel Hilbert space. So what matters is the way you fix the reproducing kernel Hilbert space. And of course, this is given. This is a probability distribution. And depending on how you define this probability distribution, you will have different problems. So this is a typical problem even in MCMC. You can look at this problem from different perspectives. You can look at this problem from the point of view of sampling. So how to choose a sampling point so that the approximation of this integral is optimal. You can look at this problem from the point of view of computational statistics. So the Q-mature error, which is the absolute difference between this integral and its finite dimensional approximation. And you can have a look at this problem from the point of view of MCMC, of Bayesian INLA implementation through stochastic differential equation. So these are classical problems that has preoccupied scientists from general perspectives.
And we cannot sample from P, but we do have some knowledge of this.
You don't, well, you don't sample from P, you sample from, you sample from M, from the domain. You choose the point.
Yeah, but I mean, when we choose the points, we choose them from which probability distribution, not P some other.
You use the Dirac delta function. So the interpolant will be just the weighted sum of the observations at the sampling point.
Ah, yeah, of course. But how do we get observations? From P or from some other?
From F. From F. This is your integrand.
I mean, F.
You observe values of F at some points,
Yes,
which are given by empirical method.
Yeah.
And the X, these points X onto which we evaluate F, they come from P. Or from
Yeah.
Ah, okay.
Yeah.
I just wanted to understand the same.
Yeah, sure.
If you go back to the picture where you have Lena, on the right side, do you have a Lena picture, the image of Lena? The first example that you showed. Yeah, that one. So on the right, do we have a constraint on the number of Dirac functions that we use?
Yes. You have a computational constraint because you can't do. Of course, if n tends to infinity, you tend to linear, right? But you have a computational problem here, and the order of computation is of n to the q, which is notorious computational pattern for any reasonable method. So the accuracy, if you take, for instance, as a reference MCMC, the accuracy will be of n to the minus something, right? But the computational cost is n to the q, which will become prohibitive for when n is reasonably large. Because most of the optimization method will, the implementation of the method will lead you to invert some metrics, right? Which is most of the time what you do. Even take, for instance, scatter plot interpolation, creeping in spatial statistics, best linear unbiased prediction. You need to invert the matrix, which is the covariance matrix, right? And this inversion becomes prohibitive when n is moderately large, because the cost of computation is n to the q.
And what is the, do you use a metric in order to judge for this?
Yeah. That's part of the talk. Here I'm just giving the idea, but actually the metric you use is the norm induced by the reproducing Kernel Hilbert space, where the integrand F is leading.
Okay. Because I think from human perspective, the distance to that image will change the perspective. Actually, if you are far away that image, it's about scale. You can definitely see it's Lena. But if you come across the screen, it might be difficult to judge. So the metric will depend on the scale.
But yeah, I understand this is a scaling problem. But that enters into another part of geometry, the fractal property of the image. So.
Yeah, from image perspective.
Yeah, from image perspective, I understand you're more interested in the geometry rather than in the metric. Yeah. So we are here. So this is well known, the way we embed our data points into a suitable Hilbert space through the mapping capital phi. And our reproducing Kernel Hilbert space, this is a standard expository material, will be the space of functions that can be written as the marginal part of a kernel. The kernel is this function capital K, which is defined on the product space of H onto itself. And to be a kernel, this function must be positive semi-definite. We don't have a whiteboard, so I guess everybody's familiar with the positive definite functions. So, which basically means that for any finite dimensional collection of points and the arbitrary set of constants, the linear combination of this kernel against the constant themselves will provide non-negative results. Okay. And so the additional property of this reproducing Kernel Hilbert space, which is fundamental to what we're doing, is that any function f defined over this Hilbert space can be linearized through the dot product of f itself against the marginalized version of the kernel, where the dot product is the dot product of the Hilbert space where we work. And there are several advantages of using kernel methods. First of all, they tell us something about the functions that we are reproducing by using given kernels. In particular, in this specific example, I'm using radially symmetric kernels, which are also termed isotropic in most parts of the statistical literature. So they just depend on the distance between any pair of points that are located over the Hilbert space. The first kernel is a compactly supported kernel, and the second is a Gaussian kernel, well known. So the first is not differentiable at the origin, and the latter is infinitely differentiable at the origin. You can see the clear difference between reproducing realizations from the first or the second Hilbert space. The first realization will be continuous with probability 1, but they will not be differentiable, and the others will be smooth infinitely many times. Okay. There are many choices in between. I just illustrated two extreme cases, the case of non-differentiable trajectories against the case of infinitely smooth trajectories. And basically, the idea is to map the data into a high-dimensional Hilbert space and to use the famous kernel trick to represent all the realizations f as a dot product against the marginalized version of the kernel. And the typical problem in statistical learning is to solve this optimization scenario. So on the basis of pairs of data, where this is the yi are my output and xi are the input, I want to find the minimum for all the functions belonging to my reproducing kernel Hilbert space of this sum, where the first component is measuring the empirical risk, and the second component is giving me a measure of regularization, and depends on a constant lambda times the squared norm of the function f of the Chicago reproducing kernel Hilbert space. And the other advantage is that I can embed data into a vector space, which allows to do many geometrical operations. So we can compute projections, we can compute angles, we can compute many things. So we can basically we're making our life easier by making our life a little bit more difficult, like going into abstract spaces. Just to give a little bit more of expository material so that everybody can go into the same page, through the kernel trick, we can represent any kernel itself as a dot product of the function capital phi, which is defined by construction as the marginal version of the kernel itself. And typically, statisticians are interested in finding estimate for the absolute difference between the functions evaluated, the function evaluated at two different points, x and y. And direct computation, direct inspection shows that this absolute difference is always bounded by the product between the norm of the function itself and the difference between the marginalized version of the kernel, where the norms are again referred to as norm in the reproducing kernel in the space. The message is that small norms are causing slow variation. And then a critical, crucial component is the representative theorem, which basically tells me that given a optimization function capital psi, which depends on n plus 1 arguments, where n is the sample dimension, the minimum is always, the solution of this minimum problem is always linear. And it can be always written as a linear combination of the kernel evaluated at the sampling point against some weights that needs to be determined according to some optimality criteria. There is a huge literature at hand from a different perspective of scattered data approximation, numerical analysis, statistics, spatial statistics, probability theory. So you will find that these statements, according to different vocabularies, different terminologies. But basically, the mathematics behind is the same.
It doesn't matter what is precise, so there is no constraint on the structure of psi is indeed psi.
Yeah, I mean there are constraints, but I didn't want to enter into mathematical details here. So you can take any optimization function which must respond to some regularity conditions, and this optimization function depends on n arguments, which are the sampling points. So the function observed at the sampling points, plus the regularization term. So it is just a general way to write the previous equation here, right? So we are here, and we're going to talk about Kernel discrepancies on Hilbert spaces. Please feel free to interrupt any time. If you think this is too technical, I can slow down. I mean, we don't need to recover the whole material. I mean, most important thing is that we understand the idea behind. So these are different approximation of Lina from our expert in image analysis. And so these different approximations depend on many things. Depend on the number of sampling points, depend on the way you locate the sampling point, depend on the way you choose the weights, right? The weights must be determined according to some optimality criteria. These weights might be constant, might be totally random, might be taken according to the optimality criteria that I will show you throughout. So it is it's a multi-dimensional problem, not easy to explain. So we define this empirical measure Qn as a linear combination of delta function, and we want to measure the Q-butter error, which is basically the difference between the state of truth and this linear combination. And in particular, I will show you how to measure the supremum of this absolute error, which is what is called the optimal quantization. This error might be big or small, might be small by chance. And there are famous results from numerical analysis for when the image is observed on the unit cube, for which you have sharp estimate for this Q-butter error. And basically, the blending of reproducing kernel Hilbert spaces into Q-butter error provides a big literature that is called the Q-butter representative. And this is the idea. The orange dots that you can see on the x-axis, this is my input space, are the sampling points. We embed the sampling points into our Hilbert space, and then we calculate the mean embedding of our kernel against this probability measure. Okay, this is linear functional. It is continuous. We can say many technical things about it, and I'm intentionally denoting this kernel mean embedding with the blue dot that you can see here. Observe this mean embedding is not a constant, it's a function, because it's a function that lives in the same reproducing kernel Hilbert space by construction. And of course, there are technical conditions so that this kernel mean is well defined. And then we define the supremum over the Hilbert ball with the unit radius of this Q-butter error, which is basically the difference between the state of truth and the approximation. And not trivial to do, but it can be shown that actually this discrepancy is identically equal to the normed difference between the two kernel mean, the kernel mean embedding with respect to P and the one embedded with respect to Q over the reproducing kernel Hilbert space. Okay. So there is a way to linearize this supremum problem over the Hilbert unit ball, and graphically this amounts exactly to this picture. So I forgot here, sorry for the inconsistency. Here I should write capital Q for the orange distribution, and then the brown dot will denote the kernel mean embedding for the distribution Q, and the discrepancy will be measured in the norm of the reproducing kernel Hilbert space. Okay. And now, for the special case, yep.
So we are not normalizing that. What is the how will we make sure that we are not exiting the unit point?
Sorry, second.
So basically, we're taking the difference. So how can we make sure without any normalization whatsoever not to exit the unit point? The difference that we're taking.
I don't understand this question.
I believe the previous slide, or not the slide. Yeah, that second equation. We're taking the norm, right? and then we so is the constraint we have to stay within the unit for, right?
Yeah.
And so with the difference like this, how can we make sure that like the vector of the difference is still like uniform?
You can normalize any observations, right? So you have a bunch of data at the sampling points.
Yes. So we have normalization factor there as well, right?
Sorry?
We have a normalization factor there as well, right?
Yeah. Yeah. So we are here. Okay. We're skipping this one. Okay. So we for the special case of the linear combination of Dirac delta functions, the picture will look like that. Okay. So we have a discretized version of the distribution Q, and the problem of discrepancy will be exactly the same, but now we are approximating the state of truth with a piecewise continuous mass density. And the big problem is, suppose that this discrepancy is identical equal to 0. So we said before, this cumulative error must be small by chance. And suppose this discrepancy is identical equal to 0. So does this imply that the distributions are the same? The answer in general is no. And the only exception is when the kernels associated with the reproducing kernel Hilbert spaces where the realizations are defined is a characteristic kernel. This is quite technical. I will skip the mathematical details, but just to give you an example, the Gaussian kernel is characteristic. Okay, so if you use the Gaussian kernel and you get a discrepancy that is equal to 0, then the implication is that the sequence of empirical measure will converge weakly to the state of truth.
This characteristic property, is it like the property of only the kernel, or the kernel plus, for example, this measure of P? So a joint property of this measure of the kernel, only property of the kernel.
No, the characteristic kernel depends on the kernel. Doesn't depend on the measure.
Okay.
Doesn't depend on the measure because I mean, I don't want to enter too much into technical details. I'm very glad to talk about them, and I can see you're tuned. But basically, you can prove that when you measure the discrepancy against characteristic kernel, this supremum over the unit ball, over the unit Hilbert ball, will not depend on P. Will only depend on Q.
Okay.
So that's the technical bridge that justifies.
Basically, why I asked, for example, so you give this example of exponential kernel, say it's characteristic. Does it mean that we can just use it all the time and we always have this property because this function is characteristic?
Yeah,
No, we cannot use it all the time.
But you will get other problems. It's a pity we don't have a whiteboard to write, but I might show you other problems that are induced by using this kernel. So just to make an example, if you implement the basic linear unbiased predictor using the Gaussian kernel, you will get exact interpolation, whatever the spatial design. So basically, you have a kernel that does not allow to distinguish with probability 1 the difference between your loop and the state of truth. So it is a very, very bad best linear unbiased predictor. So, but we can talk. I mean, we can discuss. If you have a whiteboard in your office, I'm glad to write it down.
Yeah, thank you.
And for this convergence control depends on the kernel and of course on the geometry of the domain. It cannot be so marvelous, right? Depending on the domain you work with, you can have convergence control or not. So this is a famous problem in the Monte Carlo approximation. Here the weights are independent, and the way we choose the sampling point is independent. And we have an upper bound for the expectation of the square discrepancy, which is C over n, where C is the integral of the kernel against a given probability measure. This integral is not necessarily well defined. There are some technical conditions for which it will be well defined. So if you take a Cauchy kernel, then for some probability measure, this is not well defined. This criterion is inefficient because it does not depend on the kernel itself. It only depends on the integral of the kernel against the probability measure. And there are many alternatives that have been developed in computational statistics, like greedy approximation in the continuous and discrete case. And here you have optimally weighted Monte Carlo, for which we can notice that this optimization problem can be linearized. So it can be solved by using the linear system. Okay. The question is, how can we choose the weight to improve the convergence rate? And a simple way to improve these weights is by using kernels that respond to certain regularity properties. And without entering into technical details, we define Sobolev spaces of order S, where S is a number that is bigger than d over 2, and d is the dimension of the compact set where we embedded the realizations. And this Sobolev space is defined as a set of functions whose weak derivatives up to order S are well defined, or in other words, these derivatives exist in L2. This becomes an inner space if we equip it with the linear form, the inner product, which is just a linear combination of these weak derivatives. And a kernel is called Sobolev kernel if there exists two positive constants such that the norm of the function f over the reducing kernel Hilbert space can be down and upperly bounded by the norm of the reducing over the Sobolev space itself, which implies that the reducing kernel Hilbert space and the Sobolev space become equivalent, so they are equal as set and they are norm equivalent. Correct? So under some regularity conditions, which I'm not commenting now, if my kernel is of the Sobolev kernel of order S bigger than d over 2, then the expectation of this maximum discrepancy between the state of truth and my linear combination of Dirac delta functions is uniformly bounded by this quantity. Have a look at this. If S is equal to d over 2, which we don't suppose because we're supposing that S is strictly larger than d over 2, then we get the MC rates that we have commented before. Otherwise, we have faster convergence than MCMC and quasi Monte Carlo methods. But we spend more time to compute this stuff because the order of computation is higher than MCMC. So again, this is the problem we stated at the beginning of this lecture, where we say that we're trying to reach a reasonable compromise between statistical efficiency and computational scalability. So here we can do better. Oh no, it's okay. It's okay. We can do better in terms of convergence rate, but the cost of computation is higher. The other. Thank you so much. So this was just there was something that was undefined in the presentation, which was the definition of a positive function. So this function k goes from x times x into the real number, and it is positive definite if and only if for any finite system embedded in X and for any arbitrary choice of constants, we have that this bilinear form will be non-negative. And of course, we can provide several generalizations of this definition, but for the purpose of this talk, it's enough to work with this guys. Okay. The other important advantage here, so to recap, we are faster, but computational cost is higher. But we have another additional advantage with respect to classical computational methods, which is the way to embed all this architecture into probabilistic, Bayesian probabilistic learning. And I will show you how. So we are here. We are going to discuss these kernel approximations in a Bayesian setting. Is there any questions so far?
Yeah, I somewhat missed what is the method finally. So you were mentioning the Sobolev bounds at the end. That's clear, but I mean, what is the result? So probably just to summarize, what is the method? So,
we didn't arrive at the method. Yeah, I mean, we have discussed probabilistic discrepancies within reproducing Kernel Hilbert spaces. I haven't shown you any method.
Okay, yeah, that's okay. Then
which means you are tuned. You understood the talk then, which is good. Now I'm going to talk about the method, which is the Stein method. Okay. And here it is. Here's the motivation. So here we assume the probability distribution to be absolutely continuous with respect to the effect measure. So it has a probability density which can be written in a Bayesian setting as the ratio between these quantities. Pi is called prior, capital L is the likelihood, and Z is the normalization constant. This is famous thing everywhere. So you can face this problem from different perspectives of MCMC, quasi Monte Carlo, variational inference, which is very famous in machine learning techniques. INLA, which is probably less famous to you guys, which is basically Laplace approximation through discretization of stochastic differential equations. And now, this is what I want to achieve. I want a method that allows for optimal quantization. So I want to have a method that allows to reach the lower bound for the worst case error that we have explained before in a general fashion. Okay. Then I want a method that avoids computing the normalization constant, and I want to be able to recycle the producing Kernel Hilbert space machinery because it's nice. It allows for linear form, projection, geometrical operation, as we have illustrated before. Okay, so that this is what I'm trying to achieve. And the basic principle is that if you have a kernel that possesses this property, so it integrates it to 0 for any fixed x in the input space, okay, against the probability measure, then the kernel mean discrepancy will not depend on the measure p. Will just depend on the supremum over this unit Hilbert ball, taking respect to the integrand against the measure q. This is non-trivial, and I understand it is not intuitive, but you can trust me, it is true. I mean, I didn't show it. This is classical research. I think it's a brilliant result. The idea is to find, these kernels, capital K, P, that satisfy this property are called Stein kernels. This amounts to a old dated work by Stein, 1972, who had the first idea under the Gaussian setting. So Stein was working for the case where P was a Gaussian measure. Okay, and how to find a Stein kernel given a kernel capital K? So you are reproducing Kernel Hilbert space with a given kernel. Well, the idea is to implement some operator such that retrieving, iterating twice the application of this operator with respect to x and with respect to y, we get a Stein kernel. The standing assumption is that there is a technical assumption about the gradient of the logarithm of the probability density P. And Stein proved that this operator, which depends on the gradient and the curl, okay? So you have some assumptions of differentiability on the function g and on the logarithm of P, of course. He proved that this is a Stein operator. And what is important is this chain of identities, which proves that this operator allows to get rid of the normalization constant. So this operator only depends on the numerator that we have seen before, which was basically the product between the prior and the likelihood, but doesn't depend on the normalization constant, which is a big advantage under the Bayesian perspective. So Maxime, is this answering your question regarding the method?
Yeah, I think so. Yeah.
So basically, the idea is we want to do optimal quantization, which I explained before. And we want to do optimal quantization using reproducing Kernel Hilbert spaces under a Bayesian framework and avoiding computing the normalization constant. Fair enough?
Yeah, I think so.
Okay. As an example, under some mild regularity conditions on both the gradient of the logarithm of P and of the supremum of the weighted version of the probability density, you can implement a Stein kernel just using curl and gradient operators. And you can prove that this long displayed equation is a Stein kernel. It's quite straightforward. Another important implication is that when you couple Stein kernels with kernel mean discrepancies, you will find that this supremum over the Hilbert ball can be uniquely written as the bilinear combination of my Stein kernels against these weights omega I omega G. This is a big advantage because it linearizes the optimization problem, right? And additionally, this kernel allows for weak convergence control. So whenever we get 0 from the discrepancy, then we have a weak convergence of the Dirac delta function to the state of truth. So to recap, the method allows for optimal quantization. It avoids computing the normalization constant, and it is based on the reproducing Kernel Hilbert space machine. The optimal weights are determined according to a constraint optimization, which is a typical Lagrange optimization problem that you can encounter even in the simple kriging literature or in the numerical approximation for radial basis function in the numerical analysis literature. And the solution that you will find is very similar to the simple kriging predictor. Any question? Anyone? Much time do I have? See?
Well, I think that's like 10 more minutes probably.
Oh.
Because usually our seminar is 1 hour, so we started a bit later, but already it's 4:50, so 10 minutes to 5, so like 10 minutes something.
Yeah, fine. We continue in your office. Okay? Yeah, I'm not going to leave. In particular, I've been working on what we term the Riemannian Stein kernel methods. Remember the function we want to compute here? This Riemannian Stein kernel method has been implemented many times when working over Euclidean spaces, so plane geometries, but not over Riemannian manifolds. And the problem becomes technically extremely challenging for several reasons. So the key to solve the problem when you work over compact Riemannian manifolds is to define Stein equivalence. Stein equivalence requires a pair where H is my reproducing kernel Hilbert space and tau is an operator. Okay, if we need to find this pair, this operator is from the Hilbert space into the set of continuous function from the compact manifold into the real line, and it must be such that for any measure Q, equality of these two measures is in one-to-one correspondence with this integral of the application of the operator tau to the function h against the measure q being identical equal to 0. And this must be true for any function h defined over my reducing kernel Hilbert space. So this tau h is just the application of the operator tau to the function h. Okay, so it must be true that this integral is 0 for any function h in my reproducing kernel Hilbert space. If this happens, then the pair h tau is a Stein characterization or Stein pair, and the space H will be a Stein cluster, and tau will be a Stein operator. And now we come back to the optimization problem that you have commented at the beginning of the presentation, where we have a measure of the empirical risk and a measure of the regularization. If you followed this talk attentively, you will notice that here I have two terms. In the original generic formulation, there was only one term. So my regularization depends on the sum of two regularization components, because I want to take into account for discontinuities of this function h at 0. So the regularization components can see depends on the kernel, and thus the reproducing kernel Hilbert space, on the smoothness properties of the function h. There cannot be any function, and on the fact that the application of tau to the difference between h prime and h is equal to 0. And we work under the assumption that we have a Sobolev kernel that we have defined before. Remember that Sobolev kernel induced a sharper upper bound for the worst case error, and additionally, the Sobolev kernel allows for convergence control. Here we have an assumption, Sobolev kernel of higher exponent that we have seen for a general case. This is coming from technical condition on the compact Riemannian manifold we are working with. And basically, what we can prove is that this operator defined as the curl applied to p times the gradient of h over p is a Stein, defines a Stein pair. So this result allows to define a suitable Stein pair on the basis of a Sobolev kernel and this operator. And the problem is how to define, how to find this Stein kernel. Well, it is quite simple. Once you define the operator as before, then applying twice this operator, first to the argument x prime, and then to the argument, first to the argument x, and then to the argument x prime, we get a Stein kernel. And to get rid of the additional component that we find in the regularization, we add a constant. So we define this kernel as k depending on p and sigma. Using classical theory from the representative theorem, you can prove that this interpolator can be linearized, and it depends on the inverse of the covariance matrix that is induced by this Sobolev kernel. And now we have a bunch of results. These are a bit technical. I should try to explain as best as I can. So the first result is just saying that this kernel mean discrepancy, which is this supremum over the Hilbert unit ball, can be linearized. And in particular, the kernel Stein discrepancy can be written as a bilinear combination of this Stein kernel. And the weights are uniquely determined according to the last displayed equation. So this allows for a nice computational tool to implement all this stuff. And now the problem is to see the convergence and the upper bounds for this approximation from a statistical perspective. Well, the first result is quite intuitive. That's what I would expect from a Sobolev kernel. So the reproducing kernel Hilbert spaces induced by the original kernel K and by the Stein kernel Kp are equivalent. So they are equal as sets and they are norm equivalent. And as a corollary, I'm intentionally leaving these in different colors. You can see that the supremum computed over the Sobolev ball is identically equal to the supremum computed over the Hilbert ball induced by the Stein kernel. Yeah, you can appreciate. So the quantities are the same. And the second corollary is too technical. I will skip it for you. Another non-trivial result is related to the cubature error, which basically shows that the approximation through my Stein interpolator is uniformly bounded by the norm of the function f over my Sobolev space times the field constant, which is something more technical, which depends on the geometry of the domain, the number of the sampling points, and so on. And as a corollary of this result, we can bound the expectation of this cubature error by in a similar way that we saw for when comparing with the MCMC methods. Any time left, Maxime, or should we just wrap up?
Well,
I mean,
yeah, you have 5 more minutes. Yeah.
Anytime I can wrap up because it's there is a lot of material. So just
like think of what you want to focus on in 5 minutes. That would be better.
That's a difficult question. But basically, you can illustrate this method by working on the sphere. So you can show how to implement this Riemann-Stein operator on the sphere, and using some classes of kernels, you can. Here we have 3 classes of kernels, which are the Brouchard, the Pentland kernel, which is convalley supported, and the von Mises-Fischer distribution. And you can show at which speed you attain some reliable reconstruction of the original realization of f, depending on the number of iterations and the smoothness of the associated kernel. And you can show the worst case, empirical worst case error, which responds to the upper bound that we have showed before. And then I have a bunch of more technical problems, which I'm not entering. So these problems are more related to how to characterize these kernel mean discrepancies through spectral approaches. So it amounts to use the old results by Iser Schoenberg in 1942. I will skip this part. So some quick comment about the impact of this research. So these results provide a theoretical assessment to several algorithms that have been studied from a numerical viewpoint, but not from the theoretical viewpoint. Provides foundations for variational gradient descent, allows to use good enough fit test for directional distributions, optimal quantizations of probability measure, and it is being used for sampling over Riemannian manifolds. There are several plans that can be implemented on the basis of this method. I'm very glad to talk about them whenever there is anybody interested. So my talk is finished, and I thank you for your attention.
Thank you. Yeah, colleagues, questions, please. I might start with one. So yeah, this topic is quite new for me, but compared to like classical non-parametric results, usually in like non-parametric statistics, like in density estimation or function estimation, you benefit from smoothness, but you don't have bounds on smoothness. Like for any smoothness, you usually get some rate. Like the classical non-parametric bounds is 2 times on smoothness defined, 2 times smoothness divided by 2 times smoothness plus dimension, something like that. And here we have this strong dependence, like that you strictly require that smoothness is higher than dimension over 2, which is quite a lot probably. So can you give some intuitive explanation why that happens?
Well, but I mean, if you MCMC does not rely on smoothness either. So here the principle is how to improve the statistical accuracy in terms of convergence rate for MCMC and quasi Monte Carlo methods. So for quasi Monte Carlo, you have an upper bound for this kernel mean discrepancy, which is some C over n.
Mm-hmm.
And it is quite inefficient because it doesn't depend on the kernel that you're using over the replacing kernel space. And it can be improved just by assuming a little bit more on the smoothness of the kernel, which is, I mean, to me, it's totally intuitive. It happens the same thing in this smoothness argument is recurring everywhere you implement the replacing kernel in the spaces methods.
No, my question is not, I mean, it's definitely intuitive that with increasing smoothness you obtain better rates. What is a bit non-intuitive, why you have the lower bound d over 2? Like for smaller smoothness it doesn't work for some reason. You have s greater than d over 2, right?
Yeah.
Yeah, and that's not fully intuitive, at least for me.
Yeah, but if you go below d over 2, then you become inefficient with respect to MCMC. If you have s equal to d over 2, you reach exactly the same convergence rate.
Ah, okay. So that's basically.
So you can reach it for any s, but for s smaller than d over 2, you are inefficient.
Okay. So your method is efficient for high smoothness. It's an area where, like.
Yeah.
Okay.
I mean, high smoothness. I would not say that I, because what is the dimension of your domain? You can work over the 2-dimensional sphere. Then s is bigger than 1.
Yeah, sure.
So you just take, which means that if you take this kernel, so the positive part of this difference, then this kernel is not differentiable at 0, right? So this kernel will not allow you to achieve the convergence rate that you want. But if you take, for instance, the kernel this kernel will allow you to achieve it. So it's not a big deal to implement these classes of kernels. And another reason for the Gaussian, I mean, you were commenting on why not using all the time the Gaussian. With the Gaussian, you are infinitely smooth. So how can you measure the convergence rate?
Does it become exponential somehow?
For the Gaussian?
Yeah. No, I mean that was my also question. So I don't understand what happens with Gaussian, which is infinite.
No. If you use an exponential kernel, then you are achieving inefficient convergence rate with an exponential kernel.
Why?
It's not differentiable at 0.
Okay. So then different conditions.
Yeah.
Two questions is so basically this class of methods like kernel-based methods. You assume a distribution if you're comparing the two distributions, right? And how do you so basically, I mean, if we see like word predictive models, we cannot assume a distribution, but learn by similarity. Things like the triplet laws or contrast laws, something like this. So in terms of, for me, it seems like any choice of the kernel, there's some inductive bias there, right? How the choice of how this inductive bias will affect the word predictive model that you want to build. like I would say, kernel based against distribution based against similarity based methods.
I don't know. I mean, I don't work on predictive models, but can you try to restructure the question? I don't think I get the
So the question is, so here, you're assuming that the data is lying within like a low level manifold that's coming from a distribution P. And you're trying to align a distribution Q with P, right? This is the classical method. Another like choice to do this is, we don't actually care about the distribution of the whole data points. We care about sample wise. And we want like our method to learn by similarity, contrasting like samples to each other. So I only want that the two samples, they represent the same cluster.
Yeah.
I don't care about the distribution at all.
No, this doesn't work for that case. No.
Yeah, I understand. Yeah, what I'm saying is, but this also induces like some inductive bias, right? The inductive bias is there is a distribution behind. Whereas, like if you go up to whatever reinforcement learning methods or something like high-dimensional spaces, it becomes very, very hard to induce a distribution. So the question is, like from an intuitive perspective, how would you compare the pros and cons for both of the methods? From application perspective.
I mean, from a statistical point, the way I see this is how my kernel is robust with respect to the measure misspecification. So suppose your state of truth is this capital P, and you are supposing that your realizations are induced by this reproducing Kernel Hilbert space with respect to the measure P tilde, which is another measure. Then how much are you messing up? You can study this. So I can approach this from this perspective, and the way I would approach it is from asymptotic viewpoint, which means under which class of kernels your measures, so which is the state of truth, and the other measure become equivalent. So it is a classical problem of equivalence of measures, which has been well studied by the Russian school in the 70s. Skorokhod, Gichman, Rozanov, Ibrahimov. So this is as a statistician, I would approach the problem that way. I don't know how to approach the problem the way you're doing. Never did.
Because from my experience, like if you take images or stuff like this, it is like very, very hard to generalize this kind of based methods to, detection problem, classification problems.
It is definitely.
Which means, it just shows like, and the reason why I think it's very hard to generalize is lack of high inductive bias, and this inductive bias wouldn't generalize to like outer distributions like this.
Yeah, these are challenging problems, and this is why doing math is so important, because otherwise, I mean, in terms of number crunching, we can do whatever we want, but in the moment you want to understand the accuracy of your methods, then you need to do some math around. Yep.
Regarding the Riemannian case, so in order to properly define kernel which accounts for topology and some boundary conditions, you should write an equation with Laplace time operator and solve it to get the proper kernel.
Correct.
But it somehow resembles the Stein operator you showed us, because it's also a differential form, but sort of the curvature of manifold in this case is replaced by some probability distribution. Isn't that a coincidence?
Sorry, isn't that?
I mean, how Laplace Beltrami operator and Stein operator are related? Because they look similar in some sense. So, I mean,
well, of course. I mean, of course, you depend on the Laplace Beltrami operator, because in the moment you implement the gradient and the curve, I mean, you can write any realization from your reducing Kernel Hilbert space as an orthogonal expansion of some coefficients against your eigenfunctions, which are your orthonormal basis for your
indirect space.
And so when you apply the gradient, you inevitably need the Laplace-Bertrand operator, right?
That is correct, but my question was that in order to get a proper kernel, I'd solve equation with Laplace-Bertrand operator. Okay. To obtain Stein kernel, I in turn should act with the differential operator on the kernel defined bar. And this procedure somehow resembles the original process, because the Stein operator itself, as you showed us, contains action of nabla, which is curvature dependent, and so on and so forth. So, is there a general framework from which you can just write a differential equation, and the solution will be itself a Stein kernel?
Oh wow, this is very clever. I would say no.
Okay.
I would say no. I mean, I need to, you think too fast for me, but I would say no. I need to write it down, but certainly you cannot do it on any manifold, right? So
maybe on non-compact manifolds it is difficult, but for some
you want
use.
no non-compact manifold, you're in trouble. So you certainly need compactness and you need smoothness assumptions. So for the sphere, let us make things simple. For a sphere,
yeah.
No,
I have a suggestion. So it seems like an interesting question which we can discuss after, like, you know.
No, this is a very intriguing question. Yeah, I'm gonna work over it. Thanks.
That's great.
Next talk with the new results.
Well, let's see if you invite me again after the first.
Absolutely. Dear colleagues, any more questions to Emilio? Yeah, if not, let us thank the speaker again.
Thank you.